Hi everyone, I'm Mayuresh. I'm representing Qatar Computing Research Institute. I'm here with my colleague G, and we are presenting this interesting use case for where we are using Ray platform to control traffic during an important event that is happening end of this year. And most of you, I believe, are soccer fans, so I don't need to tell you what that event is, do I? So without further ado, here is the outline of our talk. We are going to talk about what we do. We'll be quickly going over the FIFA 2022 challenge that we are addressing in this work. I'll briefly go over the conventional traffic signal control approaches and how AI or RL help us. Then we'll go into detail about how our Ray platform or RLlib help us in these solution approaches and go over some results and demonstrations at the end. All right, so we are Qatar Computing Research Institute, which is affiliated to Hamad bin Khalifa University in Qatar, and it's part of this Qatar Foundation conglomerate. And we are a group of about 136 scientists and software engineers who work on large-scale computing problems on multiple areas like NLP, cybersecurity, social computing. And within this organization, we are a center for AI. And one of the problems we work on is urban mobility, where we do problems ranging from computer vision for accident detection to building efficient software for simulation of traffic. So this is one of those projects that stem from this FIFA 2022. So here is a brief what the challenge is. So this is the map of Qatar. You can see it's like a thumb in the Arabian Peninsula. There is only one border down south to Saudi Arabia. And it's a tiny country, as you can see. It's like about 100 kilometers from north to south and 50 kilometers wide. And there will be 8 stadiums hosting the games later this year. And you can see from this map, the distance between the farthest 2 stadiums is only like 55 kilometers or 20 miles. And that means there is going to be traffic concentrated in a tiny area, right? That has been unprecedented. There will be up to 4 games a day, so and 4 different stadiums. So there will be a lot of movement across these stadiums. In terms of the numbers, we are expecting about 1.7 million people that will visit Qatar during the games. On busy days, it will be 500,000 visitors a day. To put it in context, the whole population of Qatar is only 2.8 million, so we are expecting more than 50% visitors, right? So that's the what we are trying to do is to build a coordinated traffic light control, keeping these requirements in mind so that we can help control congestion and urban mobility and show some exploration around achieving that, right? So that's the challenge. I want to next give you a little background on how conventional traffic signal control works. So general consensus is that coordinating traffic across these different traffic lights in cities, it reduces overall traffic time. That leads to reduction in carbon footprint. And there has been years of research in transportation engineering that has enabled that. But problem still remains largely unsolved because there is a lot of dynamics at play. They have these complex mathematical models that can deal with certain scenarios, but sudden changes may make them infeasible. So the question we ask is, can machine learning help here? So before addressing that, let's see what they do in little more detail, right? So there could be a fixed cycle policy wherein you let in vehicles flow for 30 seconds, followed by 5 seconds of yellow phase and followed by 30 seconds of red phase. So these are like fixed cycle policy. That obviously wouldn't work because during different times of the day, you want to have different controls. So you could do that pre-programmed schedule. Or there could be actuated controls wherein your default plan it changed according to dynamic situations like a pedestrian crossing or an emergency vehicle approaching, but these are still non-reactive changes. There are, of course, some adaptive control strategies that are based on optimal control or network of queue, and I'm going to describe one technique. These kind of react to dynamic situations, but to a limited extent. So here is one approach, one very popular approach that's called max pressure control. Here we look at the traffic flowing across an intersection. We divide it into phases, which is like a non-overlapping flows of traffic. Here an example is shown where traffic coming from west can either turn left to go to north or can go straight on to east lane. So here for this particular phase, what they calculate is something called pressure, which is difference between cars in incoming lanes, subtract from that cars in outgoing lanes. So then you look at like what's the pressure exerted by each phase, right? And whichever phase exerts the highest pressure, you'll give green to that phase. So this is a very simple approach. By nature, it's decentralized. You manage each intersection individually, and it is known to work efficiently in like grid-like networks, which are very the geometry is simple that enables the to extract everything from the algorithm. Now, going forward, we want to explore how AI can help, and we identified two ways. One is based on your previous decision, you make an informed choice, use it as a feedback, and that's your reinforcement learning. Or the other way is you want to continue your adaptive control, but augment the data by doing some forecasting. So as making decisions based on the traffic at the moment, you may want to do build some forecasting models and get that information fed in. So in case you are wondering, that picture on the right is generated by AI, and I put in like a caption to build image for chaotic urban traffic, and this is the most chaos I could find. So perhaps AI is suggesting that future won't be as chaotic. Okay, so now let's try to build some infrastructure before trying each of these approaches. So what we need, first of all, is a simulator. So if you want to do this reinforcement learning kind of training for hundreds of thousands of epochs, you can't obviously do it in a real environment. So you need a simulation model. We rely on this tool called Sumo, which is a mature open source continuous multimodal traffic simulation. And the good thing about Sumo is you can incorporate real road networks extracted from OpenStreetMaps. There is, of course, some effort needed to get them work right, but it's possible. Then we can model vehicle traffic as a fixed set of routes, or you could use something called origin-destination data, which are the macro statistics collected by urban planning authorities that tell us like what's the typical traffic from between point A and point B, and you use the simulator to create random traffic adhering to these requirements. So we get this data from urban planning authorities and use it to model traffic. Plus we carefully build traffic light phasing based on the actual real setting on the road. So for example, the picture on the bottom right is showing that there are 11 different traffic phases controlling this complex roundabout intersection on top, right? So, and then we have like multiple loop detector devices installed at different points at the intersection that kind of observe the state, like the number of cars queuing up at the lane, what's the average speed, and these kind of help us gather information, like observe what's happening. And that kind of helps algorithm make decisions based on that. So here is like an example of microsimulation in action, where there are some circulatory lanes, and there is like a overfly lanes, but there's, and based on our origin destination requirements, there is traffic that is fed into this simulator. And we have like about 68 loop detector devices that observe this, and kind of, if you are familiar with reinforcement learning, they form the state that help the algorithm make further decisions. So here is the picture of, given this environment, how we would use reinforcement learning. And this is kind of a classical diagram that you would have seen in different contexts. The environment helps us observe the state and get us reward. Now, depending on the particular algorithm, these could have different forms, but roughly speaking, state is formed by the number of vehicles that are waiting and their attributes such as wait time or speed. And reward is a combination of number of cars that you are moving, also called as throughput, or the average wait time. And then you train your policy models using this data, and RLlib provides a whole bunch of algorithms for that, ranging starting from policy gradients to Q-learning, and you can just plug and play with these different policy models. What they ultimately do is build a control policy that selects the next action, like which phase to activate, and you loop that back to the environment and see what happens next. So this process continues for multiple epochs or episodes, and in the process, you keep improving your model, right? So this was first approach, and the second I want to just briefly mention, which is based on forecasting plus your classical control. Here, this is a work done by my colleague. They build a graph convolution network to predict what the traffic would be in terms of the number of cars at each edge of the map. And then we use that max pressure algorithm using the predicted traffic instead of current traffic. So I just wanted to briefly mention that to train this complex flow attention network that we have, we could utilize PyTorch Lightning support in Ray, and this is something we plan to do in future. But now for this work, we focus on reinforcement learning. So this is about the background. Let's now go back to the FIFA 2022 challenge. So far, all the approaches we saw had a single agent controlling a traffic light. But now let's see how the FIFA scale looks like. So let's first model a day of FIFA. This is the game schedule. We are focusing on game day 2, which has now become game day 3 because of some logistical reasons. They moved one match a day earlier. So, but yeah, so we are looking at this day 22nd of November, where it will have 4 games, and these are the 4 stadiums. And the entire region formed by these stadiums contains about over 250 signalized intersections, over 27,000 junctions, over 50,000 edges. So this is the scale of the problem. We have to do a coordination between all these 250 traffic lights at the same time. And using a single super agent would make it really infeasible. This will be huge observation space. It will be a combinatorial action choices. So it's you can't hope to train such a model. So to decentralize these things, we have seen one approach already, which is max pressure, which was by nature decentralized. So here I'm just going to show some results using a controlled traffic for 1 hour of the day on this game day, and see how it fares compared to a default cyclic traffic control policy. So I have a bunch of metrics here. The throughput tells you like number of cars that arrived. So we start the simulation with 9,000 odd cars, which is based on the statistics provided to us by urban planning authorities. And we are seeing about over 5,000 cars reaching their destination by that end of that hour. The remaining cars may be still moving, or they get what we call teleported. So what happens is sometimes the simulator when it sees a car waiting too long and the traffic's like it's not moving, helping with the traffic movement, it just evaporates those vehicles. So we see a lot of such occurrences with the default cyclic policy, but max pressure control cuts it down to 0. And then that we see some impact in terms of the number of collisions. Of course, it's a simulated environment, so in reality, collisions won't happen, but this is the simulator telling us. We also report average total cumulative wait time and average speed. We see some improvements there as well. The primarily where we are using RAPE infrastructure is in building decentralized RL policies. And here what we have is each intersection managed as an RL agent. And these agents can be, so natural extension of single agent policy would be have multiple independent agents that each build policies for the intersection that they manage. Or there could be coordination, and there is different ways you could coordinate between these agents. One is by sharing the observations. So people typically learn like graph neural networks, which share the weights from your neighboring intersection. That way, you still build independent policies, but you have more observations now. Or the other way is by sharing the policy. So you, instead of training individual policies for each by each agent, you kind of combine some agents based on say geometry, where like if they have this, they see the same incoming and outgoing edges, you could combine the training data and just train one single policy for all such grouped agents, right? So, and there is, it's possible that you mix and match between these different coordination strategies. You could have shared observations plus shared policy. There are some research works on those lines. But for this exploration, we'll focus on independent and shared policy decentralization. So here is an architecture how we use RLlib multi-agent environment to help us train independent agents. So we utilize this parallel worker capability that is like natural design block provided by RLlib, wherein we can launch multiple parallel workers, each running an instance of our environment, and all the agents corresponding to different traffic lights. And there is one local worker also called as trainer that is tasked with training these policies on GPUs. So what it does is gathers, concatenates batches from all these different workers and train the policies together, and then the weights are shared to these agents again. So with this, and there is little code snippet on the right, I want to highlight a couple of points. This is standard multi-agent environment in RLlib, but what we use is what called Sumo connector that helps us connect to the simulator. There is this API called Tracy, which allows us to talk to individual traffic lights, get their state, and control their phases. So we create this multi-agent FIFA environment with this Sumo connector. And then we create policies, and this one point to look at is this line 13, where we have this policy mapping function that maps agents to policies. Over here you can see there is one-to-one mapping, but when we do this policy sharing, this map enables RLlib to understand like what agent is going to use which policy, right? And we of course have these multiple parallel workers. Here we use 10 parallel workers. That helps us speed up the training, and the training part is standard after that. So I have some quick results by looking at how the impact of this parallelism. One other optimization we have put in is since if we focus on 1 hour of traffic, there is the movement concentrated towards a stadium which is going to host a game within next hour or two. So it's sufficient to only monitor the agents on those routes and let other agents be using their default policy. So this way we can cut down on the number of agents or number of policies that we need to train to roughly about 30. And when we do this training with a single worker PPO versus we also do it with 10 workers PPO, we see a big impact in the results. So the training time remains roughly the same. That indicates that maybe with single worker we were not utilizing the computing resources efficiently. Now we can. And then now we are getting 10 times more data for training, which means like we get better throughput, better speed, cut down on wait time. So yes, so this parallelism helps us converge the training faster, right? So this is one big use case that we have utilized. And the second use of Ray is this hyperparameter tuning provided by RayTune. And here I would like to highlight this shared policy optimization algorithm contributed by our friends at Penn State University. The algorithm is called MP-Lite. And this essentially like brings uniformity to state space and action space for each agent, regardless of the intersection structure. So we are essentially training a single policy that is shared by all agents. But here the important parameter is this max distance, which controls like how far out you observe data from a intersection. So we try multiple settings for this parameter using grid search. We just run 5 parallel trainers, each using a single GPU each with this different settings for this max distance parameter. And then try to plot, like we observe for whatever, which configuration gives us the least pressure. That's the kind of the objective of this algorithm. And we observed that 200 meters is the best setting found for this parameter. And then we, in the rest of our algorithm, we use this setting. So I would like to now call my colleague, who is going to show you some results we found by trying out these different RL algorithms. And she has a cool video to play.
Okay, so it's great. So basically, we made some very quick demo. It's like 1 hour. It's between the 1 and 2 p.m. So we run the 4 algorithms, so fixed cycle, and the PPO, and the max pressure, and we do shared policy. So you can see very big differences together. And before we start, and when we visualize it in the simulation, but these are differences. We actually calculate based on the time loss. So if you are the blue, it means that there's no time loss on the traffic. It means that like a green answer is between the 10 to 60 seconds, and then yellow is about 90. And when you be the red is, so you are losing about the 900 seconds time loss. All right.
Next.
Okay. So this is Qatar. So it's very small. And as you can see, there's a flag. And then we focus on this one. So now you can see differences. So now it started running. And you can see how many cars are alive. There's some statistics. All right. So as you can see, max pressure is a little bit struggling. And the fixed cycle is the same. But as you can see, the police coordinated and PPO has a more green and the blue. It's showing that it's doing much better. And then the outcome, what we see in the policy coordinate and the RL risk learning, actually we get the best result. All right, so it's a more focus on. So fixed cycle is our ministry, and then our friend and the Ashkab, so they use a lot. And we compare in the policy coordinate, you can see some differences. As you can see, fixed cycle, you can see a lot of yellow, and then it building up some traffic. But the policy coordinate, it shows that more blue and the green, they have some red spot. Usually it's about the stadium. All right, that's good. So now we are going to a little bit diving in. So this is the Education City Stadium. It's just a few hours before game. So you can see how it goes in the traffic flow, so you can see some details. So max pressure is totally red, but around there it's more yellowish. But the fixed cycle is more red, and you can see a lot of traffic moving, but it's reddish. But it shows that, as Marish mentioned, there's a lot of the teleport cars. The car is like misplaced or disappear. And then, of course, police coordinated and the PPO. Actually, PPO is a little bit bad, but in the police coordinate is really doing well. So we are very happy with the RLlibs in the police coordinate result. So what is the conclusion? So there's three conclusions what we have. First is the traffic control is a very good use cases to using our reinforced learning, because in US, about the 300,000 traffic lights exist, and then they said 75% of the traffic control actually improve that mobility movement, and then it can reduce a lot of CO2 emission. So using this RLlib, we found that there's a lot of utility you can utilize it. And then as you can see, we can see all those scale differences. Also AI for good means that CO2 is a very, it's an attack we have to do. It's like a green world or AI, so we believe that this is the AI for good. Thank you.
Next. Next.
So we can take some questions.
Thank you. Yeah, we can take some questions now.
It's Michael. Hi. Well, thanks a lot. This is actually a wonderful presentation and validation of actually how reinforcement learning can be used. Sorry, I lost my voice. I've been talking for too long. I've been to about 6 World Cups, so I really identify with this. And I've been to both the finals and the opening games. How did you take into account the human traffic? Because there's also human traffic involved along with the cars coming in. Because any event, you have this massive amount of 60,000 to 80,000 people, waiting for the traffic light. Did you take into account the observation of the agents, not only the cars, but also the humans?
Yeah, I can take that. Okay. So we actually have this multi-modality data. They have estimates on number of pedestrians, number of people going to use buses, number of people coming by trains. We have this metro transportation. So here we focused on this road traffic by private cars. And so that kind of forms the use case for reinforcement learning. But again, to answer the specific part where there's this pedestrians also waiting, Qatar is, to begin with, not very pedestrian friendly. If you would realize when you get there. Yes, so some of these actions phases that we have, they have those built in. So there will be, whenever there is a red phase, there will be it's associated with some pedestrian green as well. So those are part of the algorithm.
Also the reason we choose to show demo education city is the design the city. So actually, once a week, no car is around. Basically, based on the tram, you have to put the car behind. So education city is they are planning to smart city, so it's a good use cases. Actually, so some traffic stay outside.
Hi, I noticed in one of the first slides you had some metrics around collisions. I'm not too familiar with Sumo, but I'd be curious, what are the factors that increase or decrease collisions and how the various approaches performed on that as well?
Yeah, thanks, Gal. Good observation. So that was a surprise to us as well, why our simulations is returning so many collisions. So it's most of it is down to the physical model of traffic movement that Sumo uses. So it's a combination of two things. One is called car following model, when you are driving, you want to maintain certain distance between the car in front of you, and there is some randomization added to it to make it more human. And there is also a lane change model, like with certain probability you want to switch to the neighboring lane. And there is sometimes this weird interplay between these models that end up giving collisions in the simulation. So that is something I believe Sumo is still working on. But yeah, so it's the high number is something we are really surprised by, and we'll also look into that. Thanks.
Presentation. Can you elaborate a bit on what are the features or like the observation state that each agent gets, and also what does an episode look like in the training?
Sure, sure. So basically, each simulation episode is formed by like this number of time steps. Each time step corresponds to some period of time, like 10 seconds. So 10 seconds in real are simulated in much faster time, but that gives us like the window for observation. So what an observation consists typically is like during that window of time, you record like number of cars that move past a detector device. So I was telling you about the number of detectors installed throughout the intersection. So they monitor like how much traffic each lane is getting, how long the cars are waiting on average for, and these kind of form the different dimensions of the observation. And yeah, depending on your particular algorithm you use, you want to use a combination of these. But yeah, so basically this gives you enough data to kind of see what's the best action.
So basically we measure how many cars are in, how many cars are out, also CO2, also emission, also waiting time. And then they're like a 261 actually have the traffic light, but when you cross it, you can find the 3 to 18 different state. So it's a kind of different phases. So each agent depends on, for example, if you belong to like only 3 phases, you get the different combination of the 3 phases of state. And if you found some traffic light that has 18 different phases, you can find all the combination. That is how it works.
And does the agent see what other agents are making decisions at the same time, or is it done synchronously or asynchronously?
So we tested that part. So we do like independently that we tested, and they come out it's not really doing well. So what we done is that it works independently, but when you go to last year, like shared weight, so they can observe the other state. So we are done already that part.
Okay, so we ran out of the time, so they'll be around, so please ask further questions personally. Thank you for a great talk, G and Mayuresh. And yeah, this is the end of the session. And please make sure that you do the survey, feedback survey. This is very helpful for our next Ray Summit. And yeah, thank you very much.
Thank you.
Thank you.